Welcome to this Rust beginner tutorial video, and in this tutorial you'll learn how to build this Unbeatable Tic-Tac-Toe game. To learn from this tutorial, you do not need to have any prior knowledge on the Rust programming language, as I will go through every concept, data type and syntax I use throughout this video, but you should have at least some knowledge of programming in some other language. There are several concepts you will learn throughout this tutorial, and by the end of this tutorial you will be able to build almost any command line application in Rust. Some of these concepts include installing Rust and setting up your development environment, the file structure of a Rust program, variables, ownership and borrowing, generics, error handling, pattern matching, dereferencing, breaking a Rust codebase into modules, adding external crates, and so much more. This video consists of two parts. In the first part, I will walk you through installing Rust and setting up the development environment for this tutorial. Then go over all the basic concepts of Rust while building this application where you can insert X and O at any position on the board. The version of the game that will be built in this part will be basic and without any logic or aesthetic. But in the second part of this video, by then you should have a good knowledge and understanding of the Rust programming language, so we will then implement the game logic and the user interface. After this part, you will be able to play with the computer from your terminal. Use the tab keys to move back and forth to different options and game positions, and use the enter key to choose the current selection. The algorithm the computer will use to get the best playing position is the Minimax Algorithm, and this algorithm is basically unbeatable. The best you can do is a draw. You can try it out for yourself after you have built the game. This being said, it's now time to start building your Rust programs, and we'll start by installing Rust and setting up our development environment. To install Rust, you can visit this website rustup.rs, and here you will download Rustup. Rustup is a tool you can use to install different versions of Rust, update or uninstall Rust on your system. To install Rustup on a macOS or Linux system, you can copy and run this command, and this downloads and runs a shell script that first installs Rustup and then uses Rustup to install the latest version of Rust. If you are on Windows, you will need to download and run the rustup init.exe file. When running Rustup, there will be some instructions for you to follow, like choosing the installation type during the installation process. After installation, if you use macOS or Linux, be sure you have cargo added to your path environment variable by running this command after the installation and restarting your terminal. You can test your installation by confirming the version of cargo and Rust compiler you have on your system. You would also need a linker that Rust uses to compile its output into one file. You can do this on macOS by installing the Xcode command line tools. If you are on a Debian-based Linux distro, you can do this by installing the Build Essential package from apt. For Windows, you'll be prompted to install Visual Studio. If you have ever worked with C, C++, or maybe Python, you may already have this installed. But if you encounter issues running your Rust program for the first time, it will most probably be that you have no linker on your system. For your IDE, there are several Rust IDEs like Rust Rover, but since VS Code is the most popular editor out there, I will show you how to set up VS Code for writing, debugging, and formatting your Rust programs. On VS Code, the extensions which are a must need for programming in Rust are Rust Analyzer, CodeLLDB, Dependencies, even better TOML and error lens. Rust Analyzer is the primary extension for working with Rust on VS Code. It provides features like code completion, inline type hints, go-to definitions, and more. CodeLLDB integrates with Rust Analyzer to provide debugging capabilities for VS Code on Rust programs. The Dependency extension helps you manage your Rust dependencies, which are called crates and are stored in the cargo.toml file. And this is the file that contains the external dependencies you use in your Rust program. It is the equivalent of the package.json file for a JavaScript program. The next extension is the Even Better Toml extension, which is responsible for syntax highlighting and formatting a toml file. Rust configuration files are mostly toml files, such as cargo.toml or rustfmt.toml. This extension provides syntax highlighting and formatting for the toml files. The last one is error lens, and this shows the warnings and errors from the Rust Analyzer right into the line causing the error, so you can get it fixed right away without having to run your program before you can see and fix the error. Lastly, for formatting, go to your settings and click on this icon, which opens the settings.json file. Then include a Rust field and set the default formatter to the Rust Analyzer extension. Now your VS Code is fully set up for Rust programming and you can start writing Rust programs. To initialize a Rust program on your terminal, enter the directory that will contain your Rust program and type cargo new, followed by the name of your program. In this case, it will be Tic-Tac-Toe. If you successfully installed Rust, followed all instructions and restarted your terminal, then this should run successfully. The cargo new command creates a directory with the program's name. You can enter into this directory and open this with the IDE of your choice. In my case, I use NeoVim. Let's take a look at the file structure of a Rust program. Inside the program, you can see a cargo.toml file. This is where the name and version of our program, along with that of the external dependencies used in our program, will be located. There are other configurations stored in this file, such as test and build configurations. But for this application, the cargo.toml file will only contain the name and version of our program and any external dependencies we make use of. Next is the source folder, which will contain all the Rust files used in the program. Within the source folder, we have the main.rs file, and inside this file we have a main function, and this function is called whenever we run the program. There is also a target directory. This contains all the compiled binary executable files and the library file from our program. A Rust program can produce multiple executable binary files and one library file. You can build this program in either debug or release mode. If you build this program using cargo build, it will be done in debug mode, and our compiled file will be stored in the target/debug directory with the name Tic-Tac-Toe. You build in release mode when you are ready to send this binary file into production. This takes longer to compile than the debug mode, but it will produce the most optimized binary file for performance and size. You can then run this program in the command line by navigating to the binary file and running it. You can see Hello World being printed to the terminal. During development, instead of building and running the binary file in separate commands, you can use the cargo run command, and this will build and run the program in one step. If you make changes to the main.rs file, you would need to enter cargo run again to build and run the current version of the application. To rebuild and run the program whenever a Rust file changes, you can install Cargo Watch using Cargo Install. Now you can start the program with Cargo Watch-X run, and this will run Cargo Run whenever a file changes. If I change Hello World to Hello Dave, this program automatically rebuilds and prints Hello Dave. For this video, I will use Cargo Run and enter a -q flag to prevent printing all the noise. This is the folder structure of the finished program. I have a lib.rs file and this is the entry point of the library crate. The main.rs file is called the binary crate as it compiles to a binary, while the lib.rs file compiles to a library file which contains all the functions, structs and enums the binary crate will make use of. If I open the main.rs file, you can see at the top of the file the statement use tic-tac-toe screen. The tic-tac-toe here is the binary crate and we import the screen module which I made public in the lib.rs file. If you are new to Rust, don't feel intimidated by all the code here as it will become clear and simple at the end of this video. In some Rust programs, you may see a directory called test at the root of the project, which is used for integration testing. Although I won't cover it in this tutorial, but in a future video where I implement a REST API with Rust, this is where I write the test for the endpoints of the API. But for now, let's look at printing values to the command line. At the current state of this program, I just print Hello World to the terminal, and now I want to change this to print a 3x3 tic-tac-toe board. Unlike JavaScript and some other programming languages, in Rust, a string literal can span multiple lines. This double quote and the text within it is called a string literal or a string slice, which is a bit different from the string collection type in Rust. This string literal here is stored in the program's binary. I will explain the difference between strings, string literals and string slices in Rust in the comment sections. But for now, let's print our tic-tac-toe board to the terminal. The tic-tac-toe board is created with a plus symbol, a hyphen and a pipe. When I run this, you can see the board being printed in the terminal. You can notice the space between the edge of the terminal and the side of the board. This is from the space right here. To remove this, use a carriage return escape character right in front of the side of the board. This moves the board to the leftmost side of the terminal, but I prefer it the previous way. You can also pass in parameters while printing to the terminal. Let's say I want to print hi, followed by the name variable. Within this string literal, I will add a curly bracket at the area I want this name to appear. Then pass in the name variable in the next argument. I can also add multiple parameters. Let's say I want to print hi blank, you are blank years old. I will create an age variable, assign this a random number, then pass it at the next parameter of the print statement. Instead of adding the variable names after the string literal, you can add the variable name directly within the curly brackets, and this should work fine. But this only works for variable names. Add a value that is gotten after some calculations, or a variable that is being returned from a function. This must be added after the string literal. Back to coding our game. The tic-tac-toe board will be an array of 9 characters, and the characters will be either an X, an O or a space. At the point of initialization, the board will be an array containing 9 spaces. This statement right here creates an array containing 9 characters, which are all just space characters. In the coming sections, I will dive deeper on variables and data types in Rust, but for now, let's just print a modifiable tic-tac-toe board to the terminal. I want to add X at the middle of the board, and this should come at index 4. So I will modify the board variable and add X at index 4. In Rust, before a variable can be modified, it needs to be marked as mutable by adding the mute keyword right before the variable name. I will then assign the element at index 4 the character X. To add the values of the board array into the print statement, just like in the last example, at the position you want the character to appear, add a curly bracket, then insert each element of the array in order after the string literal. When I run this program, you can see X right at the center of the board. You can also mutate the board at index 0 and 8 to get 3X at the diagonal. This print line keyword here is not a function but a macro. A macro is a feature in metaprogramming that allows a programmer to create a code which expands to generate other codes. A function in Rust can only have a fixed number of parameters, but the println macro looks like it can accept any number of parameters. Actually, the println macro reads the content passed into the parentheses, which are separated by commas. It then processes these and prints the processed value to the terminal. There are several other macros in Rust, like the vec macro that reads inputs passed in square brackets and creates a vector containing those values. You can also create your custom macro in Rust. Creating custom macros are outside the scope of beginner Rust programming, but I may make a video dedicated to this Rust feature. But for now, in this tutorial, you will encounter different kinds of macros and the already created macros in the Rust library. In the next sections, I will divert a little from our game to talk about variables, the different data types, mutability, ownership and borrowing in Rust. But if you are already knowledgeable on these, you can skip to this section where we read input from the user in the command line to display pieces on the board. Let's talk about variables in Rust. A variable in Rust is declared using the let keyword, followed by the variable name and a colon, then the variable type. We then assign this variable to its value using the equal sign, which is the assignment operator in Rust. The Boolean type in Rust is denoted as bool. Sometimes the type of the variable can be inferred through its value, and in such cases we do not need to add a colon and the type. Here, false can only be a Boolean type, so we can remove the colon and the bool, and this variable will still have the Boolean type. In Rust, variable names uses the snake casing, so if you have a multiple word variable name, like is game over, it will all be in small cases and the words will be separated with an underscore. There are several primitive data types in Rust, and for the next sections we will look at the number type, the character type, the string, array and vector type. We will explore more data types as we progress through this video. Let's start with the Rust number types. For Rust number types, we can either have integers or floats. Integers are whole numbers, while floating point numbers are numbers that have a fractional component, which means that they contain a decimal point. Floats are split into 32-bit floats and 64-bit floats, and these store floating point numbers of different ranges. A 64-bit float can store a wider range of numbers than 32-bit floats, but in turn consumes more memory. 8 bits make 1 byte, So 64-bit floats take up 8 bytes in the memory, while 32-bit floats take up 4. The float type in Rust is denoted by an F, followed by the size of the float in bits. So a 32-bit variable will be written like this, while a 64-bit float variable will be written in this form. If the type of the float is not specified, it will be given an F64 by default. Integers in Rust are split into signed and unsigned integers. Signed integers are integers that can be negative, 0 or positive, while unsigned integers can only take on 0 or positive integers. Basically, signed integers are integers that carry a sign, while unsigned integers have no sign. Signed and unsigned integers can be 8 bits, 16 bits, 32 bits, 64 bits, or 128 bits. Signed integers are denoted by an I, followed by the size in bits, while unsigned integers are denoted by a U, followed by the size in bits as well. The range of values for an 8-bit signed integer spans from -128 to 127, while an 8-bit unsigned integer can take on values ranging from 0 to 255. These are the range of values for all the other integer types. So if I want to specify a variable with each of the different integer type, it will look like this. If the type is not specified, the i32 type, which is the 32-bit signed integer type, will be automatically inferred to the variable. There is also the isize and the usize variants, but we shall encounter this later on in this video, and by then I will explain these two in detail. Now let's talk about the character type in Rust. In Rust, the character type represents a single character. In some other languages that have the character type, this may take up 1 byte in the memory, but in Rust, these take up 4 bytes. This means that it can represent any Unicode scalar value and not just ASCII characters. It can represent character from any language, including emojis, accented letters, and more. To contain more than one character in a variable, we use a string. In the next section, we will look at the different string types in Rust. Rust has 2 types of strings, the string type and the string slice. This is the type notation of the string type, and this is for the string slice type. Like other type, this can be inferred automatically by the compiler. To create a string with an initial value, you can use the from method of the string type and pass in a string slice. You can also call the toString method on a string slice to convert it to a string. You can create an empty string in Rust by calling the new method on the string collection type. You can also push a character to a string using the push method, or push a string slice using the pushStArrow method. The push and the pushStArrow method mutates the variable. You can see some errors here as we haven't made the variable mutable yet. To make this mutable, add the mute keyword right before the variable name, and we no longer have any errors. You may have noticed that we call the new and from method using 2 colons, but for the toString, push and pushString method, we used a dot. If you examine further, you can see that the new method was called on the string type, while the toString, push and pushStArrow method was called on the variable. To call a method on a variable, you use a dot, but to call a method on a type, you use 2 colons. Methods that can only be called on a type are mostly used for creating an instance of the type. What makes a string different from a string slice? The string type is stored on the heap and is a growable data structure. It is used if you need to modify or take ownership of the string data. A string slice, on the other hand, is borrowed and references a portion of a string. You just had terms like ownership and borrowing. This is one of Rust's unique features. You do not need to worry about this for now, as I will explain this in the section that comes after the next section. A string slice can be represented in two ways. One is through a string literal. A string literal is stored in the program's binary, and a slice that references the whole string is returned to the variable. To borrow a string from the owner, insert an ampersand right in front of the variable. You can also create a string slice from a string by first borrowing the string, then in a bracket, specify the portion of the string you wish to reference. Here I have a string and this has a value of hello world. Now I want to create a slice for just the hello portion. Hello starts at index 0 and ends at index 4. But in the square bracket we use 5 since the last index will not be included. Printing the string slice to the command line, you can see it has the value hello. Now let's talk about arrays and vectors in Rust. Arrays in Rust are used to group a fixed number of elements of the same type. The player's variable here is an array that contains two character types. Once an array size is defined, it cannot be changed, making arrays ideal for situations where the number of elements is known at compile time and will not change during the program. You can create an array in Rust using square brackets, then specify the elements of the array in the brackets, separating them by commas. The elements of an array must be of the same type. Adding a string slice to the player's array will result in an error. The array type in Rust is denoted by specifying the element type and the length of an array separated by a semicolon within a square bracket. The player's array is an array of two characters, so the type is specified as this. Back in section 4 of this video, I set the board array to be initialized with 9 space characters by adding a space character, a semicolon, and then the length of the array in square brackets. You can create an array and fill it with the same initial values using this method. So creating an array of 6 zeros will look like this. Vectors like arrays stores elements of the same type, but a vector can grow in size. If I change the player's variable from an array to a vector, I can push more characters into the player's variable. I will add the mute keyword to the player's variable so I can be able to mutate it. The player's variable was changed from an array to a vector using the vec macro. Like strings, you can also create an empty array using its new keyword and push elements to the vector using the push method. The type of a vector is denoted by a vec, followed by the type of its element in angle brackets. Like arrays, you can also create a vector and fill it with the same initial values. This is done by placing the vec macro right in front of the array. Now let's move over to the next section, where I will talk about one of Rust's most unique features, which is the ownership and the borrowing system. Each data in Rust can only have one owner. When a variable is assigned to another variable, either one of these two happens. If the data is stored on the stack like numbers, characters, and booleans, then the data is copied and the two variables point to different data. If the data is stored on the heap like strings, vectors, and hash maps, then the data is moved to the new variable and the old variable becomes invalid. You will see this in practice, but before that, let me dive a little deeper on the stack and the heap. The stack stores data whose size is fixed and known at compile time, such as integers, floats, and booleans. The heap, on the other hand, stores data that can grow in size. Data on the stack are stored next to each other, and since their sizes and location is known, copying data on the stack is simple and cheap. On the other hand, when storing data on the heap, the allocator first finds any space big enough to contain the data before storing the data at that location and returning a pointer, which is the memory address of that location. A pointer to a data is the memory address of the data's location. The pointer to that data is then pushed to the stack and the variable owns that pointer. As a result, data on the heap are unorganized, which makes locating, copying, and reallocating data on the heap expensive. So when a variable is assigned to a heap variable, instead of copying the data on the heap, Rust just makes the new variable the owner of that data and the old variable becomes invalid. You may be asking, why can't both variables own the data? To answer this, I will have to explain what happens when a variable goes out of scope. When a variable goes out of scope, if it is just an ordinary data stored on the stack, it is just popped off. But if the data is a pointer to a memory on the heap, when the pointer is popped off, the heap data is cleared and the memory at that location is freed. So if there are two variables that point to one heap data, if one of the variable is dropped, the data is cleared. Now the other variable points to an invalid data. Reading from that variable will result in an unexpected error and may crash the program. So Rust only allows one variable to own a data. To see this practically, for stack data such as integers, here we have a variable x which equals 2. If I assign a new variable y to x, the value of x is copied and pushed to the top of the stack. Now x and y point to different data. To see the behavior of a heap data, let's create a variable s, which will be a vector of the first 4 even integers. Here I want t to be able to access the data of s, so I can use them in different places. If I manually assign t to s, because of Rust ownership system, t becomes the owner of the data and trying to use s will result in an error. So how can t access the data of s without taking ownership? Instead of assigning s to t, I assign t a reference to s by adding an ampersand in front of s. Now s and t share this data, but s is still the owner. I can print the values of both variables. You can notice that in the print statement inside the curly brackets, I added a colon and a question mark. This is because a vector implements the debug trait and not the display trait. You will learn about this later in this video. If I drop the variable t, the data is still valid, so s remains valid. And I can make use of s without any errors. But if s is dropped, t can no longer be used, and trying to do this will result in an error. The act of creating a reference is called borrowing. Now, the big question is, what happens during borrowing? When I create a reference of a variable, a space is allocated at the top of the stack to store the reference. Then the memory address of the original variable is then stored at the allocated space. Now the new variable owns the pointer to the variable and not the actual data. So whenever I want to access the value of that variable, the pointer leads to the variable which I can read from or mutate without taking ownership of that data. Now if the variable that owns the reference is dropped, the reference is removed from the stack but the original data still remains valid. But when the owner of the data is dropped, the data and all its references are removed from the memory. You can read and mutate data through its references. There are two types of references, immutable and mutable references. All references we have used so far are all immutable. You can only read through those references. To mutate a data through a reference, you need to create a mutable reference by adding the mute keyword after the ampersand, and then a space between the mute and the variable name. The referenced variable needs to be marked as mutable as well. You will encounter these in the next section where I mutate a string through the input from the command line. So let's jump right into the next section. In the subsequent sections, you will learn how to read input from the command line into the program and modify the board based on this input. For now, our program will read the data I pass into it and print out that data to the command line. First, I will create a variable called input, and this will be an empty string for now. But this will be mutated by the data gotten from the input. To read an input from the command line, I will have to call the stdin function from the IO module of the Rust standard library. If this looks a bit confusing, don't worry much as I will explain modules in detail in the comment sections. But what this means is that the stdin function is located within the IO module of the Rust standard library. You may need to call this function multiple times or use other functions located within the IO module. Calling each method located within the IO module like this may be a bit verbose, so you can just import the IO module right at the top of our program by using the use keyword. If I import the stdin function, then I only need to call the stdin function below. But a better way, in my opinion, is to just import the IO module, then call the stdin function from the IO module. This enables a reader of the program understand immediately that it is an IO function. The stdin function returns an instance of the stdin struct. I won't explain structs in detail in this section, but basically a struct is a custom data type where you can store multiple data of different types in a named field. A struct in Rust also have methods which we can call on it. To read a line from the command line into a string, I will call the readLine method on the stdin struct. And since this mutates a string, I will pass in a mutable reference of the input variable. The readLine method returns a result enum. Structs and enums are two important data structures that deserves a section explaining them thoroughly, but let's continue writing our program for now. The result enum is returned in a function which has a possibility of encountering an error. The result enum has two arms. The OK arm, which will contain the data if the function runs successfully, and the error arm, which contains the error if it fails. I will explain this in detail after explaining enums in the coming section. The readLine method will fail if I somehow managed to pass in an invalid UTF-8 string. If this happens, for now we just stop the program and return an error message by calling the expect method. The expect method of the result enum returns the data if it is successful, but if it fails, it stops the program and prints an error message to the terminal. This is not the ideal way for a production application, but we'll optimize our program as we code along. I can now print the input variable to the terminal and test our program. Now when I run our program and input any string to the command line, the program prints out that same string. Now let's clean up the code a bit by grouping each procedure in this program into a function. The first function I'll create in our program aside from the main function is the printBoard function. This will take in the board array as a parameter and print it to the terminal To prevent these warnings showing up because I haven't used this function nor the parameter, this will then stop the compiler from throwing warnings at us for having a function or a variable that has not been used. This should be temporal and you should remove them as soon as you can. You can even skip adding this at all. To add a parameter to a function, first, add the variable name, a colon followed by the data type of the variable. Here, our board is an array of 9 characters. You can also add multiple parameters this way by separating each parameter with a comma. If you are returning a value, you will have to specify the type as well by adding a hyphen and a right angle, a space, then the data type of the return value. But since we are not returning anything, we can skip this. Now copy the print statement and paste in the function. The next function I will create is the getInput function. This will read the input from the command line and return a string. This won't take any parameter, but it will return a string from the input. You can then copy this and paste into the function. To return this input variable, you can either explicitly use the return keyword followed by the variable name and a semicolon, or simply place the variable you want to return at the last line of the function without a semicolon. In the main function, I will assign the input variable to the return value of this function and remove the mute keyword since I won't mutate this variable. When I run this program, it runs just like the last time, but the code is a bit cleaner. This program stops after I enter an input in the command line. To make this procedure run continuously, we use a loop. In the next section, you will learn how to implement a loop in Rust. To make a set of instructions run continuously, we do this by wrapping the statements in a loop block. To do this, first wrap the statements in curly brackets and this is called a code block. Then add a loop statement in front of the code block to make it run continuously. Now when I run the program, the code runs continuously and any data I input to the terminal is printed in the next line. And I can only terminate this program by entering Ctrl+C. For now, I'll make the loop terminate by entering quit in the command line. So I will have to create a block that will run only if the input entered is quit. In that block, I will exit the loop using the break keyword. In front of this block, I will add that the block should run if the trimmed input is equal to the string slice quit. The trim method returns a string slice with the leading white space from both ends of the string removed. Now when testing the application, if I enter quit in the input, the program should terminate successfully. There is also a continue statement in Rust that skips to the beginning of a loop instead of terminating the loop. You will encounter it soon in this video. Now we are ready to modify the tic-tac-toe board based on our inputs. But before that, let's look at structs and enums in Rust. After that, I will dive deep into the two most important enums in Rust, the option and the result enum. Here, I created a person struct that contains the name field with a string type and an age field with a U32 integer type. By the time I make use of this struct, all warnings should disappear, but I will add this code at the top of our program to remove these warnings just for this tutorial. You can also define methods on structs. Methods are similar to functions but belong in a struct. Let's define some methods on the person struct. Methods of a struct are defined within an IMPL block. After the IMPL keyword, enter the name of the struct you wish to define methods on. Let's create some methods for the person struct. First, create a new method which will be used to create an instance of the struct. This is an idiomatic way of naming the methods that create an instance of a struct, but you can name it whatever you feel is best. Since this creates the person struct, the return type for this function should be the person data type. But since the person struct to be returned is the same struct that this method belongs to, we can just use self as the return type. The person struct needs a name and an age. We can get this by adding a parameter for both in the new function. So we add a name and an age parameter, then return an instance of the person struct with the name and the age from the parameter. We can replace the assignment of the Bob variable to the return value of the new method and pass in Bob and 30 as its arguments. Since we are calling the new method on the person struct and not the variable, we use 2 colons and not a dot. Now let's create a method that can be called on a variable that is an instance of the person struct. Here I will create a method called sayName that will print the name of the person to the terminal. This method will need to access the name field of the struct. For a method to be able to access the data of a struct, the first parameter should be the self keyword. I can then use the printLine macro and pass in a string slice saying, "Hi, my name is blank." And in its next parameter, I pass in self.name. Now I can call the sayName method on Bob, and when I run the program, you can see "Hi, my name is Bob" on the terminal. If I try to use this method twice, I get an error. This is because the sayName method took ownership of Bob from the self parameter, and when the scope of the method ends, the instance is dropped and becomes invalid. To solve this, we take a reference of self instead, so we add an ampersand right in front of self, and this solves the error. Let's say you have another function called changeAge that modifies the age field of the struct. You will need to add the mute keyword in front of self to allow the method to mutate self. This will also take ownership of self, and to prevent this, you can take a mutable reference of self instead. To call the changeAge method on Bob, since this method mutates Bob, you will need to make the Bob variable mutable by adding the mute keyword. I can now call the changeAge method and pass in its new age. Notice that I can call the methods sayName and changeAge on Bob, but I can't call the new method on Bob even though it was defined in the IMPL block. This is because the new method has no access to the instance of its type. It doesn't have self as its first parameter, so it can only be called directly on the struct. On the other hand, I can call sayName directly on the person struct, but you will need to add a reference to Bob in its parameter. When I test this, they both run successfully. You can also create a struct without named fields. For example, let's create a struct called point that will contain the x and y coordinates of some points in the 2D plane. Instead of adding the x and y fields in code block, you can add the data types of x and y in parentheses. Let's create an instance of the point struct and assign it to the point variable. To access the first element of the point variable, Use point.0 and point.1 for the second element. When building a program in Rust, you may want to print the content of a struct in the terminal. For example, after changing the age of Bob, you may want to verify this by printing Bob's age to the terminal. This works for Bob's age and we can get the name as well. But what if the person struct contains 10 fields? Doing this for all fields will be tiring. An instance of the person struct cannot be added as a parameter to the print line macro since this does not implement the display trait. But we can easily implement the debug trait for the person struct. And after this, an instance of the person struct can be added in the print line macro after a little adjustment. We will dive deeper on traits in a future video, but in simple terms, traits can define the behavior and methods of a data type. Let's now take a short look at the debug trait and printing custom data to the terminal. We can implement the display trait for the person struct, but a much easier trait to implement for the person struct for debugging purposes is the debug trait. To do this, just add the statement right at the top of the struct. The drive macro is an attribute macro that makes it easy to implement some traits on a custom data type, and the debug trait is one of them. Now in our print statement in the curly brackets, add a colon followed by a question to print the debug value of the Bob variable. When I run this program, you can see that Bob is a person struct with the name Bob and age 28. If I implement the debug trait for the point struct and print the point variable to the command line, you can see the value of the point variable as well. You can also print a cleaner version of the debug value of a struct by adding a hash in between the colon and the question mark. And running this program, you will find a nicer format of the struct being printed. Now you have a strong grasp on structs in Rust. Let's look at enums in Rust. Enums allows us to define a type that have a fixed number of variants, and each arm of the enum can optionally hold data. Here is a color and input enum as an example. A variable can take on one of the red color, green, blue, yellow, or an RGB combination of integers from 0 to 255. Likewise, an input can either be a text containing a string, an integer containing an I64, or a float containing an F64 data type. You can create a color variable and assign it to one of these variants of the color enum. For the input enum, I will assign the input variable to be an integer variant of the input enum and set 2 as its data. Like structs, the debug traits can be implemented on enums to read its value in the command line. We can also implement methods on an enum in an IMPL block as well. Let's define a method on this color enum that will return the hex code of the color as a string. This method needs to access the data of the enum, so the first parameter will be self and the return type will be a string. For now, let's add the to-do macro within this function. The to-do macro is used if you want to leave the implementation of a function for later. I will need to test self with each arm of the color enum, and if self is red, I return the hex code of red, same for green and yellow. If self is the RGB arm, I will then convert the RGB value to a hex code. To do this, I will have to make use of the match operator. The match operator is a control flow operator that allows you to compare a value against a series of patterns. and then execute code based on the pattern that matches. It is similar to a switch statement in other languages but much more powerful. Here is an example using the match operator. I have an age variable. If age matches 0, I print baby. If age is between 1 to 12, I print child, and for 13 to 19, I print teen. If age is either 20 or 21, I print young adult, and for any other age, I print adult. This here is the syntax of a match control flow. After specifying an arm of the match, I then specify the procedures for that arm after the equal and the right angle symbol. Match operators are exhaustive in such that every possible value the data type can take on must be included on an arm. This last arm with an underscore is used to match any value that wasn't captured in the previous arms. You can add multiple expressions in an arm using a code block. A match operator can also return values. Let's say, instead of printing to the terminal, I just want to return a string from the age. We assign a variable to the value of the match operator and modify each arm to return a string slice. Now you have learned about the match operator, let's use it on enums. Back to the hex method of the color enum. I use a match operator on self. If self is the red variant, I return the hex code of the red color. Then do the same for blue, green, and yellow. For the RGB arm, we label the first value of the tuple R, G for the second, and B for the third. The format macro here is used to create a string with a string slice and parameters in curly brackets, just as in the print line macro. This colon and X after the variable name in curly brackets is used to return the hexadecimal value of the integer. So for the color variable inside the main function, I will call the hex method on it and print it to the terminal. Whenever a match operator is used on a variable, all possible values of the variable needs to match one of the arm. In some cases, you will just want to run a code block for just one arm. In this case, we use an if-let statement. Let's say you want to double the input only if it's an integer. Using the match operator here will be over the top for a tax on just one single arm. Instead, we use an if-let statement. Since we are going to mutate the variable, let's make it mutable. With an if-let block, if the input variable matches the integer arm, I will set input to be double the value it was. If you want to run some code if it doesn't match, you can add an else block and insert the code you wish to run. If you print the value of the input variable, you can see it's now doubled. Now let's look at the two most important enums in Rust, the result and the option enum. Rust has an inbuilt enum which is used when a value could be something or nothing. For example, we have a function that takes in a file name and returns a file with that name. There will be cases where there is no file for a given name. The function should then return an option enum with the sum variant containing the file if it exists, or the non-variant if there are no such file. So this is how the option enum in Rust looks like. It has a sum arm and a non-arm. If a value exists, we wrap it in the sum arm, and if it doesn't, we return none. The T here is a generic type. Since any type can go into the sum arm, we use a generic type T, and the generic being used is declared after the enum name in angle brackets. I won't cover generics in this tutorial, but a dedicated video for it will be made soon. For now, let's make use of Rust's option enum and remove the one we created here. Let's create a simple function that returns an integer as an enum. In the type notation of the option enum, we add i32 in angle brackets, as this states that the value within the sum arm will have an i32 type. Now we return an integer wrapped in sum. I didn't use option with 2 colons then sum here, as Rust already includes the sum and the non-variant in its prelude. This means that we can access it without accessing the option enum. You will learn about prelude in the coming sections when we talk about importing and exporting modules. In the main function, we can now use the match operator to handle cases where the output of the function was sum or none. Another important enum in Rust is the result enum. Sometimes a function may encounter an error while running, such as when reading from a file, an HTTP stream, or reading an input from the command line. In such cases, the return value of the function should be a result enum. Here's how the result enum in Rust looks like. It has an OK arm and an error arm. The result enum uses 2 generics which I'll call T and E. T is for the type that goes into the OK arm and E is for the type that goes into the error arm. If the function runs successfully, we pass in the return value in the OK arm, and if it encounters an error, we pass in the error in the error arm. To see this as an example, let's create a function that gets a user's input. I will remove this enum created here as we will use the result enum from Rust. This function can encounter an error during the process, so we return a result enum. The OK arm will contain a string type from the user's input, and we set the error arm to contain a string as well. Using a string for the error type is not recommended, as there are better ways of handling errors in Rust, which I will make another video on. We return an error arm with the error message as a string. I can now use either a match operator or an if-let statement to handle the error cases of the getInput function. There is more to the result and option enum. They both have methods such as unwrap, map, and so many others. We can even convert a result enum to an option enum and vice versa. If we go in depth on this video will be too long, so I may make a dedicated video based on this concept. Now you have learned the most important aspects of Rust. Let's complete the input functionality of our game. For the current state of our game, the input we get from the command line will mutate the board at that index. So I will rename this getInput function to getIndex from input. Since I will convert the input from the terminal to a valid index, I will also rename the input variable to index. For the getIndex from input function, this function may encounter an error while reading from the command line, so I will set the return type to be a result. If this function errors, for simplicity we insert a string to the error variant. There are better ways to handle errors in Rust, but since this is a beginner video, I am trying to make it as simple as possible, So we just set a string as the error type. For the OK variant, I will set it to an option enum with the useSize type. I will explain the reason I set this to be an option enum containing the useSize type. But for now, let's code the implementation for this function. Next, I will change this expect method to the mapAir method. The mapAir method converts the error type of a result to another type. The readLine method returns an IO error type. To convert this to a string, we use the mapArrow method. The mapAir method accepts a function as its parameter. The previous error is passed to this function as a parameter, and the function then returns a new error. Instead of passing a function, I can pass in a closure, which is basically a light version of a function in Rust. A closure begins with two pipe symbols, and in between the pipe is where we state the parameters of the closure. Since the mapArrow method passes the error into the function parameter, we label that as E. We can convert this error to a string as the return value of this function. Another concept you will learn in this section is error propagation. If the readLine method returns an error, I would like to end the function here and return the error value in this function. Assuming I assigned the return value of this function to a variable, the variable will be of the result enum type. We will now have to handle the case where the variable is the error variant, which is basically returning the error as it is, since we have already converted the previous error type to a string, which is the error type of our function. We can replace all these statements with a question mark. This will then end the function and return the error if the result is of the error variant. The variable we assigned to this function will no longer be a result enum, but will contain the value within the OK variant if the readLine function was successful. The value of this variable is the number of bytes read from the command line, and we would not be needing this. The next step will be to trim this input of white spaces at both ends of the input. You can notice we declared the input variable again and assigned it to its trimmed value. This is not possible in some languages, but Rust supports this, and this concept is called shadowing. This allows us to declare and assign a variable multiple times, and the variable uses its current assignment at that time. If the variable gotten from the command line is quit, I will have to terminate the program just as we currently do. So our return value will be the OK variant of the result enum, and we pass in none into it. Now when I call this function and get none as the option variant, that means I have no input and I will terminate the program. Next, we convert this string to an integer. To do this, use the pass method of the string slice. The pass method converts a string slice to any other type that can be converted from a string. The pass method returns a result enum, and the OK variant contains the converted type, while the error variant is returned when the type we want to convert into cannot be converted from the given string. If the input is XYZ, this cannot be converted to an integer, so the error variant will be returned. Another question is, how can the pass method know the type we wish to convert into? As you can see, we have an error saying that type annotations are needed. There are two ways we can do this. The first method is to explicitly state the return type. Here we set it to the result enum with useSize as its OK type, and for the error we use an underscore since the pass method can implicitly infer the error type. I am yet to explain the usize type. The usize type is an unsigned integer, but the number of bits depend on the architecture of the computer the program is running on. If you are running the program on a 32-bit computer, the usize becomes U32, and on a 64-bit computer, it becomes U64. This is the same case for the isize. The reason I used usize instead of U32 or U64 is that the usize type is used to index arrays in Rust. The second method of specifying the conversion type of the pass method, instead of specifying that the input variable is a result enum, after the pass method, right before the parentheses, add 2 colons and then the type of the OK value in angle brackets. The type of the error that will be returned from the pass method is the parseInt error. Now I will have to change this error to a string which will then be returned from this function. So I will use the mapError method and pass in a closure. In the parameter of the closure, pass in an underscore as we won't be making use of the error passed into the closure. For the return value of this closure, we use this string, then propagate the error. Now the input variable has the usize type. The range of integers we will allow for the input is 1 to 9, as 1 will represent the first cell of the board and 9 for the last. So if the input goes beyond this bound, we return an error with the message, the position should be an integer from 1 to 9. Since we'll be indexing the board array, the index of the first cell will be 0 and that of the last will be 8. So instead of returning the input like this, I will subtract 1 from it. Back to the game loop at the top, print the statement, enter position for x. When we try to get the index from the user and this fails, we print the error message to the terminal and restart the loop. The option and results enum both have a method called unwrap that returns the value in their sum or OK arm. To get the option within the OK arm of the results enum, call the unwrap method. You can now use an if-let statement to stop the game loop if none was returned from the input. You can also unwrap the option enum to get the value within it. We now set the character in that index of the board to x, then print the board. Running our program, I can now add x to any position of the board. If I enter an invalid position, I get this statement printed out, and when I enter quit, the game terminates. The next feature we are going to add in this game is to alternate between X and O in the game. To do that, you can first create a player's array just below the board variable and set its content to X and O. Then create a turns variable and set it to 0. At every loop of the game, we will alternate between 0 and 1. So the turns variable should be marked as mutable. At the end of the loop, we then alternate the turn by adding 1 in modulo 2. Modulo 2 implies that the highest value the turn can have is 1. If the value of the turn is 1 and turn gets incremented by 1, it becomes 2 and 2 mod 2 is 0. So we will have a clock-like operation where turn swings through 0 and 1 in cycles. When mutating the board array, we change the character we insert into it from X to the character for that turn. So if turn is 0, the player is X, and if turn is 1, the player becomes O. You can also change the print statement at the top to account for the current player. Now let's test our game. The character now alternates between X and O. An issue with our game is that we can play at a position twice. To prevent that, we will add a check that will prevent this from happening. So back to our code, if the character at that index of the board is not empty, we print to the terminal that the cell at that position is already occupied and we restart the loop. I can test the game and it works as expected. Now you have a good knowledge and understanding of the Rust programming language. Let's implement the game logic and the user interface. When this is done, you'll be able to play with the computer from your terminal. Use the tab keys to move back and forth to different options and game positions, and use the enter key to choose the current selection. The algorithm we will implement for the computer to get the best playing position is the Minimax algorithm, and this algorithm is basically unbeatable. I will go through each step in detail in this video. You will also learn how to split your codebase into modules. As of now, all our code are inside the main.rs file. As our program grows, you will need to tidy things up by grouping related functions, structs and enums into modules. If you learned so much in this video, please give it a like and share this tutorial to whoever might benefit from it. Now let's move to the next section where we split our codebase into modules in different files. Throughout the first part of this video, all our codebase were in one file. This was okay for part 1 since our codebase was little. But as our application starts to get more features, our codebase will continue to grow. In this section, you will learn how to split your codebase into different modules, and each module will be stored in their respective file. If I create a function printboard at the root of the file, I can use it directly in the main function. In Rust, you can group related functions, structs and enums into modules. Let's create a module called screen that contains all functions that prints items to the terminal and move the printboard function into this module. To use the printboard function outside the module, you will first have to make it public by adding the pub keyword before the fn keyword. Then outside this module, you can state its module name, 2 colons, then call the function. A module can contain another module. Within the screen module, let's create another module called colors, and inside colors, we create a public function called setBackgroundColor. To use this function in the printboard function, first enter the colors module, then call the setBackgroundColor function. Rust has a use keyword that you can use to bring public items within a module into scope. Assuming we have to make use of the setBackgroundColor function multiple times in this module, instead of typing the module name before the function name, at the top of the module you can bring the function into scope by typing use colors, setBackgroundColor. Now you can make use of this function like it belongs to this module. Rust also has an ask keyword which you can use to give your import an alias. For the setBackgroundColor function, I can name this function within this module to setBG. Now instead of setBackgroundColor, I use setBG. If the module contains several public items you wish to bring into scope, you can do this for each of them, or you can bring in all public items within a module using an asterisk. Although we have brought in the setForegroundColor and the setBackgroundColor function into the screen module, they are not public from the screen module. To access items from the colors module in the main function, you will have to make the module public. In the main function, you can access the set foreground color by entering the screen module, the colors module, then you can access the set foreground color function. We have brought all items in the color module into the screen module using the use keyword, but we can't access them outside the screen module directly. To enable this, add pub in front of the use keyword, and the items you bring into the scope will be made public from the screen module. This way we create module is one way of doing this. You can also create module by creating a file. The file becomes a module with the file name as the module name. But before that, let's talk about the library create and binary create, since all module we create with a file will belong to the library create. A Rust program can produce multiple executable binary files or just one library file, which the other binaries make use of. In a Rust program inside the source directory, there are two important files which a Rust program can have: a main.rs file and a lib.rs file. The main.rs file will produce an executable binary file with the name of our program. From our cargo.toml file, the name of our program is Tic-Tac-Toe. If you build our program in release mode, then navigate into the target/release directory, you can see a file named Tic-Tac-Toe. This is the executable file created from the main.rs file. If we run this file, we can play the game we created at part 1 of this video. The next file we will look at is the lib.rs file. If we create any module outside the main.rs file, this will be the entry point of the modules. You will see this in action when we build our program. When we compile this program in release mode, you can see the file libtictactoe.rlib. This is the library file generated from our Rust program. A Rust program can produce multiple executable binary files. To create another binary file from a Rust program, inside the source directory, add a bin directory and create a file with the name you want for the binary. Let's create a file called help that will just print help to the terminal. We have to create a main function for each binary file, as this will be the entry point of each binary. Then we print help. To run the help binary, after cargo run, add a bin argument and set this to help, and we have help printed at the terminal. This runs the help binary in debug mode. Let's compile our program in release mode, and when I navigate to the target/bin directory, you can find the help binary included in this directory. If I run the help binary, I get help printed to the terminal, but if I run the Tic-Tac-Toe binary, I get the current state of our program. I won't need to create multiple binaries for this program, so I will delete the bin directory. Now to talk about creating modules with files. The lib.rs file is the root of our library create. Any function, struct, enum or trait created outside a binary file will belong to the library. Each binary file can then import the library and use its resources. To see this practically, let's create a screen module that will be responsible for all resources that displays items to the terminal. I will create the screen module using a file by creating a screen.rs file inside our source directory. I will then include the screen module inside our library by adding mode screen at the top of the lib.rs file. We can create nested modules within the screen module using the file system. Let's create a choose player module within the screen module. We create a file with the file name as the module name, but this time inside a screen folder. To include the choose_player module inside the screen module, we add mode choose_player at the top of the screen.rs file. A Rust file name should use the snake casing. If I used a hyphen instead of an underscore, I won't be able to add this file into the screen module. Inside the choose_player module, I will create a public function called choose_player that will display the choose_player screen. In the main.rs file, I won't be needing our previous code anymore, so I will clean this up. Looking at the finished version of our game, in the choose_player screen, after we choose our player, the chosen player is returned and passed into the gameplay screen. This is what we will achieve from this choose_player function. We will print this screen module into the terminal and return the chosen player that will be passed to the gameplay function, which we'll create later on. But before that, you can see that the color of our board and cursor is different from the traditional terminal, and our game clears and takes up the whole terminal. This is done with an external package called Crossterm. Like other languages, in Rust you can create and use other people's code by sharing packages. The package directory for Rust is crates.io. Here you can search for amazing packages created by other Rust devs. The packages published to crates.io are called crates, since after publishing the binary and library crates are used differently. You can install a binary crate and run on your computer using cargo install as we did with cargo watch in the first part of this video. But only the library crate can be used by other programs as a dependency. Crossterm is a cross-platform library for manipulating terminals. In the next section, you will learn about the Crossterm crate and how we can add external crates to our program. To add a dependency to your Rust program, in your project directory run cargo add followed by the dependency name. Back to our code base, first thing I'll do is to bring in the terminal module from Crossterm into our program scope. In the terminal module, there are two important functions we will make use of: the enable raw mode and disable raw mode function. If we visit the documentation for the Crossterm crate and head to the terminal module, you can find the raw mode section that explains what happens when we enter raw mode. In raw mode, our program will have control of the behavior of the input over the terminal. In the main function, since we are dealing with input from the command line, our program may encounter an error externally either from the operating system or somewhere else. Because of this, we add IO result as the return type of the main function and use an empty tuple as the OK type. I may not have explained tuples in the first part of this video, but basically it's a compound type that can store elements of different types. If X is a tuple containing an integer, a string slice and a boolean, to access the first element we use x.0, x.1 for the second and x.2 for the third. An empty tuple is called a unit, and this is the return type for a function that doesn't return anything. We will call the enable raw mode function at the beginning of our program and disable raw mode at the end. If our program runs successfully, we return an OK with the unit type as its value. The enable and disable raw mode functions both return an IO result, so we can propagate the error if any of them errors. To test the terminal raw mode, I will sleep the program's thread for 15 seconds so you can see what happens when we enter and leave raw mode. When I run the application, our program is still running because the thread is paused and every key I type does not display on the screen. But as soon as the 15-second mark is reached, the raw mode is disabled and our input is displayed on the screen. In between the enable and disable raw mode function will be the game loop. Inside the game loop, we will call the choosePlayer function and display the choosePlayer screen. Recall that the lib.rs file is the root of our library crate. To use the library crate from any binary file, just as we imported the terminal module from Crossterm, we will make the screen module public and import with useTicTacToe screen. We can't reach the choosePlayer function from the screen and choosePlayer module, as the choosePlayer module is not public from the screen module. If I make this public, to use the choosePlayer function from the main.rs file, at the imports after the screen module, I have to enter the choosePlayer module, then access the choosePlayer function. This is long and doesn't look good. Instead of making the choosePlayer module public, we can expose every item in the choosePlayer module with an asterisk and make it public from the screen module using the pub keyword. Now from the outside, it will seem like every public resource from the choosePlayer module belongs to the screen module. So in the main.rs file, we can call the choosePlayer function directly from the screen module. In the choosePlayer function, we print out the choosePlayer screen. Our screen is 19 rows and 32 columns. The /r is the carriage return character and this starts the write of the new line at this point. We end the string with a new line and a carriage return. You can copy this from my GitHub and paste in your code. When I run the program, you will see the choosePlayer screen being printed to the terminal. Let's talk about the return type of the choosePlayer function. In the finished game at the choosePlayer screen, we have two players to choose from and the chosen player is used in the gameplay screen. We can also quit the game at this screen. This means that from the return value of the choosePlayer function, we should be able to get the chosen player and confirm if the game can continue. Since the player can either be an X or an O, instead of using the character, we can create a player enum and implement some methods for that enum. The player enum will belong to the models module. So I'll create the file models.rs and include the models module in the lib.rs file. Next, I will create a player submodule within the models module. Therefore, I will have to create a model/players.rs file. I will then include the players module in the models.rs file. In the players module, I will create a public enum called player, and this will take on the values X and O. There are some methods the player module should have, like getting the character value for each arm of the enum, and also a method for getting the other arm of the enum, which will be used to change tones. So add an implementation block for the player enum and define a public char method. This will take a reference to self and return a character. Then use a match operator on self, and if self is the X variant, return the character X, and if it is O, return O. Next is the others function. This should be public too and take a reference to self as well, but returns self. Self represents the player enum. So if self is X, the other player should be O, and if self is O, the other player should be X. I want this player's enum to be accessed directly from the models module. So back in the models module, I import all public resources into the models module and export them as if they belonged directly to the models module. Back to the chosePlayer function, I import the player enum with useCreate models player. If you look at the main.rs file, we imported the screen module with Tic-Tac-Toe, but in the chosePlayer module, I did that with create. This is because the main.rs file is a different create from the lib.rs file, so we import items using the lib.rs create name. But because the screen and models module all belong to the same library create, we can start the import with create instead of Tic-Tac-Toe, which is the create name. We start an import with the create's name only if it's an external create. The create keyword starts from the lib.rs file, so we move down to the models module before we can access the player's enum. There is also a super keyword used to access a module one level above the current module. To access the player's enum with super instead of create, we will have to go 2 modules above to access the models module, then the player enum. We won't use this here, but along this tutorial, we will have to access a function in a parent module. Then we use the super keyword. For the return type of the chosePlayer module, since we'll be dealing with the input from the terminal, I will have to import the I/O module of the standard library and return an I/O result. The OK type of this result will be a tuple containing the chosen player and a boolean indicating if the game can continue. I will add a to-do macro at the end of the function for now to remove the errors for not returning the correct item. In the main.rs file, if the chosePlayer function errors, we return it. The next feature to add is to clear the screen when the game starts and when the game ends. We will handle this using Crossterm. To execute a command in Crossterm, we will have to wrap it in its execute macro, so we import this macro from Crossterm. The first argument we pass into the execute macro is the stdout struct from the IO module. Stdout stands for standard input, and it is responsible for writing to the terminal where the program is running. We have imported the IO module above, so we create a mutable variable which I will name stdout, then assign this variable to the return type of the stdout function. The stdout function returns an instance of the stdout struct. You can then pass in the variable as the first argument in the macro. Now import the clear struct and the clear type enum from the terminal module of the Crossterm library. You can see I added self in the curly brackets. This imports the terminal module itself. Since we called the enable raw mode and disable raw mode function from the terminal module, we still need the terminal module to be in scope while still importing some resources within it. Crossterm allows us to manipulate the cursor in the terminal. Before we begin any clearing or painting, it is best to move the cursor to the top left of the terminal. So import the cursor module as this contains the resources we need to do this. After the stdout variable, add the move2struct from cursor and pass in the values 0 and 0. To clear the terminal, add the clear struct in the execute macro and pass in the clear type enum. The clear type enum has about 6 arms, but the two we will need here is the all arm and the purge arm. The documentation says that the all variant clears all items on the screen, while the purge clears all items including the history. Using only one of them doesn't get me what I want, so I will use the clear type all followed by clear type purge. And this clears both the screen and the history in every terminal I tested this application in. The execute macro returns an IO result, so I propagate the error. After using the stdout variable in the execute macro, I would like to ensure that what I want to be displayed to the terminal must be displayed at this point by importing the right trait and calling the flush method on the stdout variable. I will also like to clear the terminal when our game terminates, so I will copy and paste this at the end of the loop. Before testing this, at the chosePlayer function, return an OK and pass in any player and true in a tuple. In the main function, after the chosePlayer screen, we pause the loop for 10 seconds then break the loop. In your terminal, run your program, and after this compiles, you can see the chosePlayer screen taking up the whole terminal. And after 10 seconds, this should clear. In the reference application, the foreground color is cyan, but our application still uses the terminal's color. In the next section, we will style our output using Crossterm. In the chosePlayer function, let's move the println macro to its own function. From Crossterm, we import the same resource we did as in the main.rs file, but also include the color enum and the set foreground color struct from the style module. I will add this statement at the top of the file to prevent all the warnings. Before printing to the screen, I get an instance of the standard output, pass it in the execute macro, purge the screen and set the foreground color to cyan. After the print screen function, I then flush the standard output. Let's now test our application. When I run the application from the terminal, you can see that the board now uses the cyan color. The next feature we will add is navigation using the tab keys and selection using the enter key. We should also be able to terminate the game with the escape key. The tab keys moves the cursor to specified cells in the terminal. We are going to create a struct called tabs which will contain all the cells the cursor can move to. Then implement two methods, the next and the prev, for moving the cursor around the cells. The tab struct will belong in the models module, so in the models directory, create a tabs.rs file, then add the tabs module in the models module. I will also add all public items in the models module to this module and make them public from here. In the tab.rs file, create a public struct which I will name tabs, and this will make use of a generic type T. The tab struct will contain two fields, an index field with the isize type, and a positions field, which will be a vector containing tuples whose first and second elements are U16 integers, and its third argument will be the generic type T. Now let's implement some methods on the tab struct. Before that, I will add this statement to prevent warnings on my screen, but I will remove them after I have made use of these structs. The first method to implement for these structs is the new method. This should be public and will take in a parameter which I will call positions, and the type of this parameter should be the same as the positions field in the struct. The new method should return an instance of the tab struct, so we set its return type as self. Inside this function, we create and return an instance of this struct and pass in the positions from the parameter and set its index field as 0. The other methods needed for this struct are a position method that returns the position of the current tab, a value method that returns the value of the current tab, a next method that increases the index by 1, which moves the tab ahead by 1 step, and a prev method that decreases the index by 1, which moves the tab behind by 1 step. The position method finds the tuple at the current index in the position vector and returns the first and second element of the tuple in a tuple. You can notice that the index is converted to a usize, since only a usize can be used to index a slice. The index field is an isize for a reason which you will see soon. The value method returns a reference of the third element of the current tab, and you can see that the return type of this method is a reference of the generic type T. The next and prev method takes a mutable reference to self, as this changes the index of the struct. To perform operations on integers in Rust, the integers need to be of the same type, so the length of the position vector is converted to an isize and assigned to the variable len. The index of the struct is then increased by 1, but we do this in the modulo of the length of the vector. The remainder operator ensures that the increment does not reach the end of the vector. If index plus 1 equals the length of the vector, then the remainder operator changes this to 0 since x divided by x has no remainder. So if the index reaches the end of the vector, calling the next method will send it back to the beginning. For positive integers, a remainder operation is the same as a modulo operation. Let's now look at the prev method. It does the same thing as the next method, but instead of increasing the index by 1, it decreases the index by 1. The plus len and remainder len ensures that we do not go beyond 0 when decreasing the index. X plus len remainder len is the same as x modulo len. You can learn more about the remainder and modulo operator if you are a bit confused on this. Back to the choose_player module and the print line macro of the print screen function. If we start counting from 0, the position of player X is at the column 17 and row 13, and player O is at column 22 and row 13. So in the choose_player function, create an instance of the tab struct through its new method and pass in this vector as the positions. Then assign the instance to a mutable variable which I will name tabs. From the Crossterm library, import the event module, and from the event module, import the event and the key code enum. Now we will create a loop, and in each loop, we will listen for an event from the terminal. If the event comes from a recognizable key, we handle the event. If not, we continue the loop. After the tabs variable, create a loop and add the clear screen operation, the print screen function, and flush the standard output inside this loop. Next, we listen for a key event. This read method returns an IO result whose success value is an event enum. If the event enum is of the key variant, then we should run our key binding operation. Inside this iflet block, we perform a match operation on the code of the key that was pressed. If the key is a tab, we move to the next tab. If it's a back tab, which is the shift plus the tab key, we go to the previous tab. If the key is the enter key, we return an OK containing a tuple, and the first element will be the player at the current tab, while the second element of the tuple will be true, meaning that we can continue the game. The value method returns a reference to the player, but we want to return an owned player enum. We can't just change the return type of this function to be a reference of the player, since there is no reference parameter it will come from. You can watch my video on lifetimes to understand why. Instead, we implement a clone trait for the player enum, so we can clone the player and return an owned value. We can easily implement the clone trait for a struct or an enum using the drive macro. So let's go to the player module and drive the clone trait for this enum. Back to the choose player module, we can now call the clone method on the player. The next key we'll create an operation for is the escape key. When the escape key is pressed, instead of returning true, we return false so our game loop from the main function knows we want to quit the game. If any other key is pressed, we just continue the loop. The last operation we will add in this function is the cursor highlighting. When we move through tabs in the game, we want the area the cursor is on to be highlighted. To do that, first, from the Crossterm library at the style module, import the set background color, the reset color, and the print struct. After the print screen function, add the execute macro and propagate its IO error. Then pass in the standard output, move the cursor to the current position of the tab, then set the background color of that cell to red. After setting the background color, it won't have any effect until we print a value at that position. So using the print struct, print the character of the player at the current tab. After printing a single value, the cursor moves one step to the right, so we reset the color and move the cursor back to the cell of the tab. Now let's remove the thread slip and run the application. We can now move between the X and O tabs, but when I press enter, our application terminates, and so does the escape key. You can also notice we have the cursor beneath the highlighted tab. To remove this, import the hide and show struct from the cursor module. Before the loop, hide the cursor using this statement, and at the end of the loop, You can display the cursor again with this statement. Now running the application, the cursor is no longer displayed, and when our program terminates, you can see the cursor again. It's now time to work on the gameplay screen. The enter key terminates the application because after the choose_player function, we just break the loop. The return value of the choose_player function is a tuple containing the chosen player and a boolean indicating if the game can continue. Rust has a pattern matching feature that allows us to destructure tuples and structs. To destructure this tuple, we assign the return value of the choose_player function to what looks like a tuple. We set the first value to a human player variable and the second to a continue game variable. Now let's create our gameplay screen. I will create a file and name it gameplay.rs. And just as the choose_player module, in the screen.rs file, I will add the gameplay module and expose all the public resources in this module to the screen module and make them public. In the choose_player.rs file, I can now remove this statement as the warning should be gone by now. Then copy all items in this file and paste in the gameplay.rs file. I will rename this function to gameplay. The gameplay function will receive the human player as a parameter and its return value should contain the winning player. I will then wrap the player in its return value in an option enum. The reason for this is that the winner can either be player X, player O, or none of them if it's a draw. When the enter or escape key is pressed, I will set the winning player to none for now. Above the tabs variable, let's create a mutable board array. Just as we did in part 1 of this video, we initialize the board array with 9 empty characters. Now you can modify the print screen method to accept the board array, which it will use when displaying the state of the game to the screen. In the loop, we then add the board to the print screen function. Next, we modify what we print to the screen. This is the string literal that will be displayed on the screen. Before we test the current state of our application, let's go to the main.rs file. If continue game is false, we break the loop. Next, we call the gameplay function and pass in a reference of the human player. Considering that this returns a result, we can propagate its error. The gameplay function will return a tuple containing the winning player and a boolean indicating if we can continue the game. Now let's test the current state of our application. When I run the application, I can alternate the tab between X and O, and I can exit the game using the escape key. When I choose a player, I have the gameplay screen displayed. When I press the tab and the back tab key, which is the shift plus the tab key, I still alternate between X and O. This is because I am yet to add the tabs implementation for the gameplay screen. This still uses the tabs from the choose player screen. I can also exit the game using the escape key. In the gameplay.rs file, while creating an instance of the tab structs, I will update the content of the vector to be these tuples, as this is the position of the cells of the board, and the third element of each tuple represents the index. In the highlight tab section, I am getting an error since the return type of the value, which is a number, does not have the chars method. So I will remove this, but the content of the highlighted cell should be the element of the board at the current index. Therefore, I will use this to index the board array. But to do so, I will need to dereference and convert to a usize type. I can also set the generic type T to be the usize in the tabs instance using the turbofish syntax, and I no longer need to convert the tabs value to a usize. Now when I run the application and choose a player, I can move back and forth through the cells of the tic-tac-toe board. When I press enter, our game still terminates. So that is the next item we will handle. When the enter key is pressed, for now I will just set the content of the cell to be the character of the player. Let's test the application and choose the player X. When I press the enter key, X is added to the cell of the board, and I can use the tab key to navigate to a different cell. Now let's test with playing with O, and this works just fine. It's now time to add the game logic and implement the Minimax algorithm, which the computer will use to get the best playing position. In this section, we will implement two utility functions. A function that returns the winner of the game and another that gets the best playing position for the computer. They will all belong in a utils module. So in the source directory, add a utils.rs file and add the module in the lib.rs file. Then create two files, getWinner.rs and getBestMove.rs inside the utils directory. In the utils.rs file, add two modules and export their public contents in the utils module. In the getWinner.rs file, create a public function which I will name getWinner, and this will take in a reference of the board as a parameter and return an option enum containing the player enum. You can import the player enum from the models module. In the getWinner function, first I will define the winning combinations of the tic-tac-toe game. Next, I will assign the character value of player X to the variable X and the character value of player O to the variable O. Then for each winning combinations, if X matches any combination, we return player X as the winner, but if O does, we return O as the winner. If none of them does, we return none. Now let's work on the getBestMove function. In the getBestMove module, create a public function with the same name as the module. This will take a reference of the board array and the computer player and return a usize type. So we will have to import the player enum from the models module. The best move will be calculated by going through every empty cell in the board. Calculate the score for each cell using an algorithm and return the index of the cell with the highest score. For the implementation of the getBestMove function, I created mutable variables for the best score and the move index, then set it to the minimum value a signed 32-bit integer can have, and set the move index variable to 0. While calculating the score for each empty cell, Our program needs to play on the board, so we create a mutable copy of the board variable from the parameter. Now for each cell, if the cell is empty, the program plays at that cell, then uses the Minimax algorithm to calculate the score for that cell, then clears the cell it played in. Now if the score of the cell is greater than the best score, we set the best score to that score and update the move index to the index of that cell. It does this for all empty cells, and when this is done, it returns the index with the best score. To use the Minimax algorithm, we will need to check the winner at the end of each possible gameplay. So we import the getWinner function, and since this belongs to the utils module, one level above the module we are in right now, we can import this using the super keyword. So what is the Minimax algorithm and how does the function work? Let's look at a one-step winning position for X and assume X is the computer player. If X plays at index 6, it wins instantly, so it assigns the cell a score of 1. If X plays at index 7, the game isn't over yet, so O plays next. If O plays at index 6, then X plays at index 2, and this leads to a draw. Therefore, the cell at index 6 is given a score of 0. If O plays at index 2, then O wins the game, so a score of -1 is given to the cell at index 2. Since it's O's turn and O is not the computer player, it chooses the cell with the least score, so it plays at index 2. Therefore, the score for X playing at index 7 is -1. If X plays at index 2, the game isn't over yet, so O plays at one of the 2 remaining index. If O plays at index 7, X plays at index 6, winning the game in the process. So 1 is given to the cell at index 7. If O plays at index 6, X plays at index 7, which leads to a draw. So a score of 0 is given to the cell at index 6. O chooses the cell with the least value, so it plays at index 6. Therefore, X playing at index 2 has a score of 0. At the human player's turn, which is O's turn, the best playing position is the cell with the least score, but for the computer player, which is X in this case, the best playing position is the cell with the highest score. X playing at index 6 has a score of 1. X playing at index 7 has a score of -1, and X playing at index 2 has a score of 0. So X chooses index 6, the cell with the highest score, as the cell with the best playing position, and wins the game. Now it's time to implement this algorithm in our program. The Minimax function takes a mutable reference of the board, a reference of the computer player, and a boolean indicating if it's the computer's turn to play. The function then returns a 32-bit signed integer. From the computer player, we can get the human player by calling its other method. We are going to compare the winner player with the human player and the computer player. When comparing the winner and the computer player, since the computer player is a reference of a player, to compare the two, I will have to clone the computer player. I am still getting an error while comparing the winner and the computer player. This is because right now the player enum cannot be compared against itself. To make this possible, I will have to drive the partial EQ trait on the player enum. So in the player module, just as we did for the clone trait, I will add the partial EQ trait as well. Since the winner player is an option enum wrapping the player enum, I will have to wrap the computer player in the sum arm. Now if the winner is the computer player, the algorithm should return a score of 1. On the other hand, if the winner is the human player, the algorithm should return a score of -1. If there are no empty cells in the board, then the game is a draw and will return a score of 0. If there is no winner and there are still empty cells in the board, the other player then plays in the next empty cell and calculates the score for that cell. If it is the computer's turn, it chooses the cell with the maximum score, and if it is the human player, it chooses the cell with the minimum score. Now we have gotten the algorithm for the program to choose a cell. Let's implement this in the gameplay module. Back to the gameplay module, before the loop, I will create a variable that keeps track of the player's turn. I will set the first turn to the player X and make the variable mutable. The computer player will be gotten by calling the other method. Now after the enter key is pressed, I will update the turn. Right before the key binding, the two operations left to add are to check if the game is won, play at an empty cell if it's the computer's turn. To check if the game is won, first we get the winner from the getWinner function. If there is a winner, we return the winner in a tuple contained in the result enum, and the second element of the tuple should be true, since we should proceed to the end menu screen. If there are no empty cells, then the game is draw and we return none as the winner player. Next, we add the feature for computers to play when it's their turn. So if it's the computer's turn, we get the best move by calling the best move function and pass a reference to the board and the computer player. The best move function is imported from the utils module. After getting the best move, we add the player character at that position in the board array. Now alternate the turn and restart the loop. When testing the game, we can play with the computer and the computer plays really well. When the computer wins or draws, our game terminates. The feature left to be added is for the tabs to move only on empty cells and automatically move the cursor to an empty cell after the computer plays. To do this, when the enter key is pressed, instead of just calling the next method, we wrap this in a loop, and we will break from this loop only if the cell is empty. I will do this for the back tab key as well. After the computer plays, we find the next empty tab if it exists, just as if the tab key was pressed. Now we can play the game with the computer, but when we lose or draw, the game terminates. It's now time to add the end menu screen. Inside the screen folder, create an endmenu.rs file. Add this module to the screen module and export all of its public resource from this module. I will copy the codes from the chooseplayer.rs file to the endmenu.rs file, then rename the chooseplayer function to endmenu. The result enum from the return type will only contain a boolean. When the game ends, a message is displayed in this box, and this depends on whether the game is won, lost or drawn. To know which message to display, the end menu function needs to accept two parameters, the winning player and the human player. The end menu screen also displays the board we played in, so we will have to add the board in the function's parameter and return the board from the gameplay function. In the gameplay function, I will add an array of 9 characters as the second element of the tuple in its return type. Then at every line we returned a value, add the board variable as the second element of the tuple. Back to the end menu module, its print screen function will take a reference to the board as a parameter, since this will be displayed to the screen. Replace the print line macro with this, and as you can see, we will have two tabs, Restart and Quit. The Restart tab starts at column 16, row 15, while the Quit tab starts at column 17, row 17. So we modify the vector we pass to the new method of the tab struct with this new data. The third value of the tuple in this vector will be another tuple, and this will contain the text of the tab and a boolean. When highlighting the selected tab, we set the text to the first element of the tab's value. When the Enter key is pressed, the value that will be returned will be the second element of the tab's value. For the Escape key, we return false. In the main.rs file, the gameplay function now has a board in the second element of its tuple, so we update this. If we can't continue the game, we end the loop and our program terminates. We can now call the end menu function and pass in the winning player, the human player and the board. This returns a boolean indicating if we can continue the game, so we assign it to a variable. If the game is restarted, our loop restarts, but if not, we end the loop and terminate the game. Now let's test our game. Our game quits and restarts just as it should. What is left of our application is to display a message on this box of the screen. To do this, in the endmenu.rs file, under the print screen function, use a match operator on the winning player. If the winning player exists and is the human player, then the statement becomes you win and the color becomes green. If the winning player is not the human player, the statement becomes you lose and the color is magenta. If there is no winning player, the game is a tie and the statement becomes it's a tie and the color is yellow. We then destructure the tuple from the match operator and assign to the variables, statement and color. Add this statement below and this should be the print statement using the color inside the box. And this is how it should look like. I will also like to color the border of the box. To do this, in the execute macro under the set foreground color, add the next 6 lines. Now you can play the game, and we have successfully built a tic-tac-toe game you can play with your computer. But before building for release, let's remove all the allow macro we used in our code base and handle any remaining warnings. To build an executable binary file from your Rust program, run cargo build but with the release flag in your terminal. Your compiled binary can be found in the target/release directory of your application, and you can run the binary. Thanks for watching.